Hey guys, it's Init 6 team here again. Again, you'll recognise the faces around the table. We've got Rick, Derek, John, Abdel, and myself, Daren. And we've got a bit of a special episode today. We, as members of the team, what we're really keen to make sure is that we stress to everybody who watches and listens to us that you're up on the fundamentals of everything that we do in networking. It's really, really key. And it's not just about learning the new stuff, but it's also being a student of the history and understanding where this stuff's come from and why it's shaped the way it is. You know, I guess, guys, this is important to us all, right? We need to make sure that everyone has that full understanding of networking to be able to drive this on into the next generation.
Yeah, there's, the foundational pieces of this. You have to know your history, know where you came from. That kind of sets and plots the course to where you're going, and it helps you avoid the errors of the past as well. And who we're talking to today is one of the great thinkers and contributors of our generation, of the internet, of networking. Somebody, I mean, this is really, really special.
Yeah.
When growing up, I mean, when we talk about technology, come up, Bill Gates, still Steve Jobs, but you know what? Even those guys had founding fathers. So today, we're going to introduce the founding father of network engineering. So we hope you like it. I'm honored to introduce Dr. Vint Cerf, recipient of the Presidential Medal of Freedom, the Queen Elizabeth Prize for Engineering, the Turing Award, and the IEEE Alexander Graham Bell Medal. Now, this is along with other prestigious awards, but first, before we get started, I'm going to ask Mr. Cerf, how are you feeling? How are your family recovering from the coronavirus and so forth? Just start with that.
First of all, I was, let's see, I was tested positive around the 24th of March. So it's been a few weeks now, 2 or 3 weeks. So I'm feeling much better. The symptoms were fairly mild, but it was exhausting. I mean, it's a debilitating kind of disease. But I'm back to more or less normal. I'm working from home like everybody else. But my basement office is a place where I'm very comfortable working. I'm often here. So I'm pretty much back to normal. Thanks very much for asking.
I'm glad you recovered. And the wife is good?
Good to see you.
The wife is good too?
Yes, she's okay too. So we're both, I'm pretty sure that we're no longer, what is the right word? Communicable. Okay. Or infectious, or whatever the right word is. Yeah.
Well, thanks for joining.
Thanks.
Brilliant.
I mean, first off, to echo Derek's sentiments, I mean, this is such an honor speaking to you. So thank you very much for taking the time, and even though you're still in recovery, for continuing to spend the time with us. So, I mean, the internet has long ago reached the level of being critical to businesses. Well, those same technologies in today, like what y'all have experienced with the corona, are now essential for society to continue to function in social distancing and quarantine. Back in 1974, did you guys ever envision playing such a critical role in society like this?
Well, probably not. Remember that our motivation at that time was to design a technology that would serve the Defense Department for command and control. Interestingly, that meant video and voice and data and so on, which we all today take advantage of just as we are right this moment. The second observation, though, is that even then, we had several years of experience with the ARPANET, which is the predecessor of Packet Switch Network, and demonstrated the utility of packet switching for computer communication. And even then, in that general, not 74, but in the later 1970s, we were experimenting with packet voice and packet video. Not very much of it because the data rates were not sustainable. The backbone data rate of the ARPANET was 50 kilobits a second. Can't get a lot of video down that path. But we were anticipating the need for that, and the hoped, of course, that there would be technology that would come along that would increase the capacity of the system, which it did. In the late 70s and early 80s, we started to see optical fiber becoming available at much higher data rates than the traditional dedicated telephone circuit. The other thing I wanted to observe is that the people who were doing the actual work on this Defense Department project were graduate students at universities and research institutions, and they were using the technology while it was being developed. And their uses of the technology included electronic mail, distribution lists, things like that, remote access and capabilities. And even though we didn't have a World Wide Web available, we did have time sharing available. And so remote access to computing resources were used for what I will call civilian applications. Now, keep in mind, during that period of time, or certainly anyway in the early 1980s, bulletin board systems were popular in the general public before any of them had access to the internet, which doesn't really occur until the very late 1980s and early 1990s, and then reached something of a crescendo in the mid-1990s as the World Wide Web becomes more widely available, and Netscape Communications goes public, and the stock goes through the roof, the boom is on. So I would say that in the 1970s, we were seeing potential applications in the civilian sector, in addition to our Defense Department motivations. But I don't think that we could have imagined, or we certainly would not have claimed that the system as it existed then would be suitable for putting half the world's population online. Today, of course, it's the 2020s. We're in the middle of the COVID-19 epidemic. We're forcing people onto the internet in order to achieve this separation. Work from home is becoming more common. And so the internet has managed to sustain this increased demand, which is pretty satisfying when you think about it.
I was going to ask that question actually. That you've kind of seen this take up kind of rocket through the roof, really, yes. Especially over very recent weeks. And touch wood, everything seems to still work largely. I mean, I guess there are services that fall over, and there are issues here and there, but on the whole, you must be
continuing to work.
Well, several things have been happening over the past several years that I think inform my reactions anyway. The first one, of course, is if you know anything about how the internet works, it's astonishing when a web page responds. I mean, you know, when you spin something to Google search and a web page pops up, and you think, my God, that's amazing, considering all the stuff that had to work, you know, to make that happen. I'm always amazed. The second thing that was surprising is the bet that the company Netflix made to move from its distribution of DVDs to online streaming of video. And of course, that was only possible because of the increased capacity of cable, internet protocols running on cable or on optical fiber nets like Fios from Verizon. So that was a pretty interesting bet. And it tended to be asymmetric because the streaming tended to require bandwidth going from the servers to the users. The second thing that facilitated that, of course, was the content distribution networks like Akamai, for example, and Google, of course, has its own versions of that, as do others. So placing the sources of the video streams closer to the users to avoid overloading the global internet also turned out to be very important. The thing which is surprising is that we can do what we're doing now because that requires symmetric bandwidth. And many of the systems that were designed for home use were not designed with symmetry in mind. In fact, if anything, there was some resistance to offering symmetric capacity because the telcos and the cable cos didn't want users to run businesses from their homes. And they didn't want servers running from people's homes. But now, of course, given the attention that's been paid to remote access to education and working from home and the like, and having conference calls like this, we're seeing the value and the feasibility of this more symmetric capacity. I will put in a small plug for Google Fiber, because when Google got into the fiber game in Kansas City, one of the things it did was to offer symmetric gigabit per second bandwidth. And the symmetry was understood to be useful not only for high-speed streaming and conference calls like this, but also to reduce delay and latency for people who were playing computer games. And eventually, of course, Google has taken advantage of that and now offers its own set of computer games online with low latencies, partly because of the high speeds at which in both directions that these underlying systems support.
Any of those
That was symmetric. That's good.
Any of those innovations that you just mentioned, did they shock you? Has anything ever came out and said and made you go, man, I never thought of that? You know, we're talking about Netflix, we're talking about anything Google's doing, what have you. Anything make you, sit back and go, man.
Lots of things. I mean, keep in mind that I'm not the guy that thought up all the applications that people are putting the network to. It's sort of like Bob Kahn and I figured out what the streets should look like and some of the rules for driving on the street. Everybody else gets to decide what vehicles to put on it or what buildings to put on the side of the road. So there are a few. Certainly when the iPhone showed up, that was a really interesting marriage of technology. Probably the most significant part, well, two parts. One of them was the camera, which promoted people taking pictures and sharing them. And the other one was simply the ability to run apps on the phone, to have sufficient computing capability in your hand to be able to run fairly sophisticated applications or to get access to them on the internet. So I saw that particular arrival as a mutually reinforcing technology. The mobile phone made the internet more accessible, and the internet made the mobile phone more useful. That's one. The second one, earlier on, of course, was optical fiber networking and the capacity that offered. That was clearly exciting, and I wasn't an expert in that space, so I was very happy to see that technology arrive. It sort of arrived approximately at the point where the internet gets turned on. We were talking about January of '83, and the optical fiber stuff was starting to become useful to MCI, for example, where I was at that time, in order to drive dedicated and switched telephone circuits to much higher speed. So that's an earlier one. And more recent examples, of course, are the streaming video. And the fact that it actually works at scale was a surprise. And I remember thinking about Reed Hastings and his Netflix. That it looked like a really high-risk bet that there would be enough capacity to carry video. Now, the next thing that's coming, though, and is very visible, are the data centers and the kind of computing capability that we now have available. We called it at Google warehouse computing in the early days anyway. You build this giant building and you just fill it with things that would have been laptops, except they're not. They're in racks stacked from floor to ceiling. But now there are new capabilities coming that I certainly did not anticipate. Some of the TensorFlow machine learning hardware, which accelerates machine learning applications, really required some deep insight into how those neural networks could function, how they could be trained, and how they could be made to operate quickly. Of course, the next thing that's coming down the pike is quantum computing, and although there's a lot of hyperbole associated with it, Google's work and others show that it is feasible to build these things. Whether they will be useful in a range of applications remains to be seen. There are no quantum computers that I know of anyway that will do useful computations yet. We can demonstrate that those computations are showing evidence of higher capacity, higher compute capacity than we would get by emulating the quantum computing on an ordinary binary computer. So we know that we have hardware that will do something that's in excess of conventional systems, but what we don't have are applications that produce useful optimizations, for instance, and that, of course, is the the primary target is optimization, or in one case of Shor's algorithm, of course, the ability to do factorization, which triggers all kinds of concerns for people whose cryptography is dependent on the difficulty of factorization. The good news there, of course, is that there are other mathematical puzzles that have already been proposed as an alternative to the work factor of factoring the products of large primes. And so the National Institutes of Standards and Technology are already evaluating post-quantum algorithms in order to make sure that our information can be kept secure for long periods of time, since a lot of the cryptography is intended to work over a period of decades. So that means you have to be thinking decades ahead about what capability will be available, and then to build crypto which is capable of defending against those decades away capacities.
That's awesome.
It's and it's known that this decade would be the decade of quantum computing, quantum communications, and assurance of post-quantum cryptography protection. Anyway, so that's definitely something we're looking forward to see.
Well, for some of your viewers, if they're interested in certain kinds of mathematics, they might want to put their toes in the water, so to speak. Lattice mathematics, for example, offers a variety of interesting cryptographic problems that are not subject to Shor's algorithm, and some of those are showing up. There was something like 36 different proposals that came into NIST, and I think they winnowed that down to 18. Of course, they're working to get to a much smaller number, so they'll end up with 1 or 2 proposals or recommendations.
Yeah, so it's an absolute honor, Vint, to meet you and talk to you. You're going to hear that a lot. So, yeah, so my question is, us folks at Init 6, we are absolutely committed to spreading the word about network programmability and automation. But we really firmly believe this is one of the best ways we can help future generations of network engineers evolve and survive in our ever-changing industry. So based on that, what advice can you give us to help us spread the word, get it out there?
So that is a very good question. And I will tell you that in the early days of software-defined networking, I considered this to be a kind of a marketing term. It sounded like hyperbole. My reaction was, well, wait a minute, you know, all the routers I ever met were all running on software, so what's different? Although I will say that after digging in a bit deeper and looking at the sort of raw switching engines that were being built, and then were then being programmed in order to be packet switches, that I came around to recognize that there were a couple of important things, consequences of that particular design, where the bulk of the functionality really was realized as software on top of an underlying switching engine. So one network that I'm familiar with the Barefoot Networks, had a big 14 billion transistor chip. It's a really big chip, which could roughly had something like a pipeline or 32 processors, and could execute something like 4,000 instructions per packet flowing through at line speed, because the packets were processed with a pipeline. So the programming language for that was called P4. And I am by no means a P4 programmer. The reason I highlight this is that for many years, it was possible for students of networking to get into the insides of routers, because mostly it was open source, and you could dive in because a router was just any other programmable processor. But then they became specialized, and special companies built equipment like Cisco and Juniper, and they didn't let you in, and they certainly didn't hand out their source code. So there was a generation or two of network engineers who learned how to control and configure the devices, but didn't actually get to look inside to see how the software worked. Now with software-defined networks, there's the possibility anyway to introduce a new generation of engineers to the details of how routing and how packet processing could work or does work, because they have to be able to see the P4 or other programming languages that make the routers run. So that's good news, because it means that we will have a new generation of engineers who get to see inside and to observe how these things actually function or don't function, which of course is the other side of the coin, and that's where bugs that show up or vulnerabilities show up and attacks get made. Again, the software helps people understand the nature of the vulnerability and to learn how to defend against them.
Something that we're all big believers of is the understanding the fundamentals. So, you know, understand how switching works, understand how routing works, understand what happens to packets as they flow through a network. Don't just rely on an easy button to go and configure stuff in a GUI, because you need to understand how the thing works. And I think that, from what you're just saying, that takes that visibility a step further, I suppose.
Now, there is a controversial argument that I've made in the past and been criticized for. That is that I believe that engineers, network engineers, need to be taught how to write malware. And the reason that I think they need to understand how malware gets written and to experience writing it is that they don't get that exposure. How the hell are they going to write software that defends against it? And some people would say, well, you're training terrorists or something like that. And my reaction to this is, no, you have to understand how the bad guys work in order to figure out how to defend against it. So I'm a big fan of actually teaching this stuff. I'd also teach ethics and say that you should not use this. It's like a locksmith class. You know, you tell people, I'm going to show you how locks work. I'm going to show you how to pick locks. You're going to need to do that in the course of your profession, but there's some ethics associated with this. And oh, by the way, if they catch you doing something illegal, you might end up going to jail. Somewhere along the line, we need to introduce similar kinds of not only ethical, but maybe even legal constraints about what people are permitted to do in the course of their work in the networking space.
That's a brilliant point. That is a brilliant point.
Yeah, exactly.
That's one we haven't made, and I like that. You know, that's a brilliant point right there.
Taking from that thread, Vint, is you wrote back in 2002 on RFC 3271 about the internet for everyone. And you stated in that you believe that we must have the freedom to speak and the freedom to hear. So that's I'm quoting from the RFC 3271. Do you still feel that way as well right now, especially when some countries like China is actively discussing splitting the internet and putting a hard border around sections of the internet, and also creating their own IP-like and protocol, and putting their own shut-up mechanism that to isolate the network or isolate specific hosts if that is actually counteract their internal policies or something like that. What do you think about that?
Well, first of all, I much prefer an open internet, one in which people are free not only to find information, but to share information and to build applications and to explore things without much constraint. However, having observed the kinds of abuses that are showing up in the internet today, I think we cannot speak of a totally unregulated environment or an unmanaged environment. I think that there have to be penalties for people who harm others in the online environment. I don't much like the idea of drawing national boundaries around pieces of the internet, although politically speaking, it may be impossible to avoid that, because a country often has the authority to control all of the assets that are within its borders that are part of the internet. So, for example, shutting down the internet happens in various and sundry countries. In the Cameroon, for example, shut the internet down during elections because they were worried about it. Abusive disinformation, among other things. That's using a giant sledgehammer, to kill a fly. It's not. I would not argue that shutting the internet down is the right way to deal with this problem. But there is a problem of misinformation and disinformation, the abuse of social media and the like, and we do have to figure out how to cope with that. And we have to figure out how to cope with it on an international basis, because the perpetrators may be in one jurisdiction and the victims in another. And that could easily cross national boundaries, which leads us to the need for cooperation across those international boundaries, across jurisdictional boundaries, in order to maintain some kind of order. Now, the extreme case of that is what you see and hear from China, which built this Chinese firewall and is offering hardware from Huawei and ZTE to implement a variety of constraints on the users of the internet, whether that's filtering or censorship or tracking and observation. Those are things that those of us in the West are not very happy about and don't believe are necessary. But the other side of that coin is that law enforcement has to be able to exercise its authority in order to protect people, in addition to people learning how to protect themselves by adopting good practices and using two-factor authentication and other kinds of tools, being attentive to phishing attacks and so on. We have to provide those people with tools. So it's going to be a really interesting decade, this next 21st century decade, to try to find the right balance to protect people from harm while at the same time preserving what we all would agree are their human rights to access to information and to express themselves. But one of the things that I started working on in 1998 was an interplanetary extension of the internet. And this is now going extremely well. Our prototype software was fielded in 2004 on Mars, both on the surface and the orbiters. The more fully developed protocol suite is now running on the International Space Station. And as the 2024 initiative Return to the Moon, at least from NASA, and the Gateway program and the Artemis effort, we'll use those interplanetary protocols. We've given them away. They're standardized by the Consultative Committee on Space Data Systems, so all the spacefaring nations have access to them if they want to use them. There's open source available. I'm very excited about that because although I won't see the end of it, I think during this next decade, we will see a significant expansion of the use of networking in space. And I think that'll be a lot of fun to participate in.
I want that job.
That's
really cool. That job.
really amazing.
That's going to be awesome. Yeah.
Go ahead, Rick.
So I just want to wrap it up by saying, it's truly humbling to speak with someone who I think for a lot of us take for granted some of this stuff that you've created and been a part of, the internet and things. And to just be in the presence of that is really humbling, and your contribution to our profession is, well, thank you. So,
thank you.
Keep in mind, keep in mind that lots and lots of people, including you, have made the internet what it is. So this is not a one or two person thing. Bob Kahn and I did the initial work, of course, and we helped to fund it from the Defense Department. But it was getting lots of people excited about this and contributing to it that made it what it is today. So I can thank you for your role in it as well. And I do have to run, but thanks a bunch for a chance to chat.
Thanks so much for your time.
Take your time.
Take care.
thank you.
Thanks, Vin.
Bye for now.
Bye-bye.
And then Matt.